Hello, and welcome back to the course. So today we're gonna talk about automorphisms of the disk, of the unit disk. So that's subsection 3.5.2 in the book. All right, so recall what an automorphism is. So an automorphism in our setting is a mapping, so automorphism of some domain, U, is a biholomorphism from U to U, right? So it's a holomorphic map, F, that is invertible, so it's bijective, and its inverse is holomorphic, right? So let's compute the automorphism group of the unit disk, right? And we gave this a name before, or gave this, had notation for this. All right. So let's start with very specific automorphisms. So given any A in the disk, so any complex number in the disk, let's define these linear fractional transformations that actually do take the disk to the disk, as we'll see. Also, you'll see it's an exercise. So for each A, we write down this formula. So z minus A divided by 1 minus A bar, so conjugate of A, is times z, right? So this is a nice linear fractional transformation. One thing that you can immediately see is that it takes A to 0, right? So it takes 0 to minus A. That's also an easy one, right? And well, let's make this into a proposition. So we have, okay, so this guy is an LFT that takes A to 0. It takes 0 to minus A. Those are totally trivial. Maybe a little bit slightly less trivial, but still trivial. Let's compute the derivative. So you can look at what the derivative is at 0 and at A. These formulas are sometimes useful. Now, this mapping takes the circle, so the boundary of the unit disk, to the circle. So it takes the unit circle to the unit circle. This works for any A, and it takes the disk to the disk, right? So and any point in the disk ends up somewhere in the disk, right? So it's a mapping that's onto the unit disk, right, and preserves the unit circle, and it's a linear fractional transformation, so it's actually it is one-to-one. It's not constant. And this is actually not too hard to prove. So you can prove that it's an automorphism by just proving this guy, which is just computation, right? So proving that its inverse is phi sub minus A, right? That's going to actually be an inverse, right? That proves that it is an automorphism. There is the inverse, right? It also really proves that it's one-to-one. If you can find an inverse, then it's one-to-one. So all of these are just computation directly from the formula. There's nothing deep going on over here. And the proof is an exercise. It's just, an exercise to do a little bit of algebra. All right, so let's see what one of these guys does. If I look at put something, some image in the unit disk, and it's I didn't originally mean the dot, which is really marking minus 0.4 to really be on that particular area of this animal, but it ended up that way anyway. So we have this picture, and I also drew some circles and lines and see what this map does, right? So A is the negative, and in the disk it's right over here, and that goes to 0, right? All of these circles, right? They still go to they still go to circles because this is a linear fractional transformation, and so we saw that takes circles to circles, and straight lines go to circles, or circles can also go to straight lines, right? I mean, it's linear fractional transformation preserves a set of circles and straight lines, right? So this is what one of these guys does, right? All right. So now it turns out that that these guys, if you do use for all different A in the disk, that's almost all the automorphisms. It's not quite all the automorphisms. I could also rotate. So in more explicitly, what it means is that if we have a function which is the automorphism, it's of this form, right? So the e to the I theta multiplication by e to the I theta is a rotation, right? So there can be a rotation and then one of these automorphisms, and that's the set of all automorphisms. So given basically the theta is giving us an angle, so if I know the point is going to 0 and then the angle of the rotation, I know the automorphism. There are no other automorphisms, and for any real theta and A in the unit disk, well, this is an automorphism, right? So this completely gives us the automorphism group, and it's actually kind of interesting, right? It's you think that there are lots and lots of holomorphic functions, but suddenly if I want them to be automorphisms of the disk, suddenly there's not that many, right? There's very few, and that's fairly typical. It's hard to be an automorphism of a domain. It's actually, the disk actually has quite a few, relatively speaking. So sort of tells you about the class of holomorphic functions, and that it is actually somewhat restrictive. So if we want global automorphisms, so automorphisms of the entire disk, yeah, then there's very few. Interestingly, local automorphisms, so changing the change of coordinates in some neighborhood, so not specifying what neighborhood goes to what neighborhood. Yeah, there's a lot of those, right? I mean, any holomorphic function with a non-zero derivative gives you a local automorphism, right? But here we're requiring a global one that goes from D to D. All right, so let's prove this, right? So let A, and this is actually not going to be a dA in the but it's almost going to be the A. But let's suppose that it's we let A be f of 0. So now if we take this A and we look at phi sub A, and we compose with f, well, that gives us a G which takes 0 to 0, right? Basically, f takes 0 to A, and phi sub A takes A to 0, right? So we have this G, and this G is an automorphism. We know that the phi sub A is an automorphism. We know that f is an automorphism. Composing two automorphisms gives us an automorphism, right? Still bijective, still has a holomorphic inverse, right? So now, just like in the proof of Schwarz, and this is something that we'll keep doing over and over, we can divide out this 0 at the origin, right? I mean, it's basically, if you write the expansion around 0 for this function g, right? Some power series expansion, well, it has no constant term, right? So all the terms are a multiple of z. I can factor out a z and still get a power series, at least one z, right? So I can write it as z times some h, right? All right. Well, now applying Schwarz to this. So Schwarz's lemma, it says that for all z in this in this disk minus 0, I have that h is less than 1, right? It's really g of z is less than or equal to z, right? That's the thing that's or modulus of g of z is less than or equal to modulus of z, right? That's what Schwarz tells us. All right. Now, h itself can have no zeros. Why? Well, for any non-zero z, right, when z is actually over here, then we have to g of z is not zero, right? Because g is injective, and it already takes 0 to 0, right? So it cannot take any other number to 0, right? So that means h cannot be 0 for anything non-zero, right? Now, why is h of 0 non-zero? Well, because if I look at h of 0, what is h of 0? Well, h is holomorphic, so it's continuous, right? So it's the limit of its values as we tend to 0, right? So it's this limit over here, well, which is precisely the derivative of g at the origin. Now, g is an automorphism. It has an inverse. So we do have that its derivative cannot be 0. It wouldn't have a holomorphic inverse otherwise. So therefore, g prime at 0 is non-zero, right? That means that h of 0, which is g prime at 0, is not 0, right? So h is never 0 on the unit disk. Now, g is biholomorphic. That means g inverse is holomorphic. In particular, it's continuous. That means that if I pull back a compact set, it's compact, right? I mean, this is something that's continuous functions push forward compact sets to compact sets, right? So the forward image by a continuous function of a compact set is compact. Well, g inverse is continuous. So if I push forward k, right, for some compact set subset of D, right, then that has to be compact. What does this mean? It means that if modulus of z goes to 1, so if I have, let's say, any sequence of z's that goes to 1 in modulus, then I have that the modulus of g goes to 1, right? And it's an exercise follows from this, right? Now, what does that mean? Well, it means that h is gonna do the same thing, right? Because I mean, as you're approaching mod z equal to 1, I mean, g and h are kind of the same. Well, quite the same thing, but they get closer and closer and closer, right? So therefore, h goes to 1 as, or I mean, modulus of h goes to 1 as modulus of z goes to 1. Right. All right. So that means that h has to attain a minimum. Right. I mean, it cannot. It's always less than 1, less than or equal to 1, right? And it goes to 1 as we approach the boundary. Right. Therefore, well, it had better be, right? It cannot, be bigger, right? It could plausibly be, in modulus, it could be smaller, right? And this minimum is non-zero, right? Because, well, I mean, it's never zero, right? Right. So, meaning, I can look at 1 over h, right? It's never zero. That attains the maximum, right? So maximum principle. H is constant. So actually, whatever the minimum is, it's the constant, right? So it attains the minimum everywhere because it's constant. All right. So therefore, G is just, well, G is Z times H. H is constant. So maybe let H be some constant alpha, right? Now, because this is an automorphism, if alpha was in modulus less than 1, then it wouldn't be. It would actually take the disk to a smaller disk, right? So the only way that this is going to be an automorphism is if alpha is of modulus 1, meaning it's equal to some eta I theta, right? And now we're basically done. So we have, what do we have? We have this equality over here, right? We have that eta I theta z, right, which is what G is phi sub a composed with F. And therefore, if we apply phi sub minus a, which is the inverse of phi sub a, right, we'll get on the right-hand side over here, we get F. And, well, we just apply it to this side, see what we get. And so what we do get is this formula over here, and a little bit of computation, right? You have to basically factor out that, pull the e the I theta out in the right way, so that you put it into the form that you want. Right, so this is why I was saying it's not quite that a is not quite the a that we want to end up with, but it's, that's what it is, right? This number over here, which is just a direct computation, right? But this number over here, right? The e to the I theta is the right e to the I theta. All right, and that's it. That's the proof. So it's really just maximum principle, right? I mean, Schwarz's lemma is maximum principle in some sense, right? But it's one version of, or it follows one consequence of maximum principle. All right, so there are some useful exercises to try. So one thing, those a fairly simple exercise that tell you something about the automorphism group. You can take any points to any other point, but you can also take right. What you can say is you can actually swap 2 points. That's also possible, right? So you can take, given any A and B in the disk, you can find an automorphism that takes A to B, and that also takes B to A, right? So it swaps the 2 points. You cannot do like that you take 2 points to any arbitrary other 2 points. That doesn't work. But you can find one that swaps. Maybe the more common thing to apply is that given any 2 points, you can always find an automorphism that takes one to the other. That's the common thing that's often needed, right? All right. Now you can, by applying an LFT and working out what's happening, you can also, anytime that you have something that's equivalent to D, right, by an LFT, such as the upper half plane, right, you can figure out what its automorphism group is, as again it's going to be LFT because you're just composing LFT. So for example, for the upper half plane, it's really different model for the disk. it looks like this, where all of these guys are real numbers. And if you had the, if it was something not, some domain that was not, not equivalent via an LFT, but you had just some other biholomorphism, then you could again figure out the formula for the automorphism group. Anything that's equivalent to the unit disk, the automorphism group of it, given that the equivalence with the unit disk. And we'll actually show that later on in the course. We'll show that any domain which is not the entire complex plane and doesn't have holes is actually equivalent to the unit disk. Although finding that equivalence is that's a different trick. That's much harder than showing that one exists. All right, now. Another fun exercise, and this is actually, I want to point this one out because it's kind of a typical thing to ask on an exam, especially something like a qualifying exam or something like that. So, suppose that there's ways to state this in more generality, but let's suppose that we take some neighborhood of the closed unit disk, right? And let's suppose that we have a function, and that's defined holomorphic and defined on this neighborhood of this unit disk. And let's suppose that it takes the circle to the circle. And you're supposed to find a formula for f, right? Find a general form for f. And the hint is that you want to use the phi sub a. It's not going to be phi sub a times rotation. It's going to be more complicated than that. But it's still actually reasonably easy. It's the one thing that basically we don't have here. You want to sort of follow the same ideas, or same circle of ideas. No pun intended. But you don't have that this is an automorphism. This doesn't go back, right? So, and basically what you do is you try to divide out by phi sub a, right? So that's the hint, right? Divide out until you get something constant, and then you get the formula, right? You have to make that work, right? You have to figure out how to write that. All right. So hopefully I haven't ruined anyone's qualifying exams, but this is such a well-known problem that it's it's probably it's not ruining it by giving a hint. Sometimes the hint is part of the problem, it's to prove the formula. All right. So, right now another exercise, and I'll state it as a lemma here. In the book, it's stated as an exercise, but there's an invariant version of Schwarz lemma. So Schwarz lemma is really about functions that go from 0 to 0, but that's kind of special. But you can really again take any point to any other point by an automorphism. So you could ask about Schwarz lemma that just works for any functions going from the disk to the disk, right? And that's the Schwarz-Pick lemma, right? Which is basically Schwarz lemma with automorphisms thrown in, right? So the only thing here we're asking is for the function to be holomorphic from disk to disk, and then we get these two inequalities, and and they end up being this and this, right? So you have an inequality both for the values and the derivative, right? And if an equality holds, for any when z is not zeta. So over here, any z in the disk, but over here you want to, if equality holds for z not equal to zeta, because otherwise, yeah, that it always holds otherwise, right? But if it holds for some distinct z and zeta, so at one point here or at one point here, then you get that that f is actually an automorphism of the disk, right? All right. Conversely, if f is an automorphism, these things are equalities for all z and zeta, right? And again, as I said, proof is an exercise. Now, it does, before I said that we had we bounded the f prime at 0, right? That was the what Schwarz told us, and I said that we don't really have a bound elsewhere. Well, we do in terms of, right? I mean, it can, as you approach the boundary, it goes to infinity, right? But we can actually find the right sort of bound there by using automorphism or by using this lemma, right? And that's this guy where, I mean, basically I just moved this over to here, right, and multiplied both sides to get an estimate, right? So if we know that f of a is b, right, then it has this sort of pleasing formula over here, right? All right. So that gives us that's an estimate that works at every point, but it does depend on the point and on the value of the function at the point, right? Now, again, if you have given this a and b, right, and given this bound, if you have an equality, then here's the actual formula for this automorphism, right? You can easily, because it has to be the thing that takes a to b, right? So there is some rotation involved because it's not unique, right? But yeah, here's the formula, right? Okay, so that's it for this section, and actually that's it for this chapter. So next time we're gonna move to chapter 4, and we're gonna look at the logarithm, which is really the thing that makes a lot of the applications of complex analysis work, right? And it's the exponential is a really nice function. Its derivative is never 0, so we want to try to invert it. But unlike the real exponential, the complex exponential is not invertible. It's locally invertible, but not everywhere invertible, right? So it doesn't actually have sort of a nice inverse, but the complex logarithm is a thing. It's just not sort of this classical function that takes a unique point to that takes a point to some other one unique point, right? So it's really gonna take a point to infinitely many points, but it's fine. We're gonna be fine with that. All right. So we were already kind of fine with that. That was the argument was that, right? So we were already kind of okay with this. All right. So that's next time. So see you then.